Hello, this is Jack Jackson. In this video or section of the notes, we will be working through some examples, the same example given in the previous section where we did a hypothesis test, one sample z-test using the critical value method. And this one we will work through it using the p-value method instead. The p-value method has some distinct advantages, so it is actually my preferred method of the two possibilities here. So the classical test statistic method that we did in the previous video is we were comparing x-bar values to x-bar values, or usually z-scores of those values to each other. So we're using critical values, which are z-scores, compared to a test statistic, which is a z-score. And so what we had to do is compute boundary values, A and B, or critical value lower and critical value upper, which are sample mean values corresponding to probability of alpha, and compare it to the measured x-bar value, or possibly its z-score, for the sample. In this video, instead, we're going to look at the p-value method. And what we do in the p-value method, instead of comparing x-bar to x-bar or z to z, what we're going to do is compare probability to probability, or area to area, under the PDF. So we compare probabilities. So what we end up doing is computing the probability, which is an area under the PDF curve corresponding to the measured sample mean, and compare it to alpha. So what is a p-value? A p-value is the probability of getting the result that you actually got in the sample, or something more extreme, if the null hypothesis were true. So we end up comparing the p-value directly to the alpha value to obtain our conclusion about the hypothesis test. I would dare say that understanding the meaning of a p-value is perhaps the single most important thing in an introductory statistics course. It's extremely important that you understand what a p-value is. So let's just read this one more time. What's in the red box is the thing, actually probably the most important thing in the whole course. A p-value is the probability of getting the result that you actually got in the sample, or something more extreme if the null hypothesis were true. So if we are computing the probability of getting a sample mean as far or farther away from the hypothesized mean as the measured sample mean, given that the null hypothesis is true, that's going to be a p-value. In this case, more extreme means further to the right or left of the mean, since we're dealing with a two-tailed test, an example that we did in the last example. So maybe I need to actually go back and look at that example, because we're doing the same one. So let's back up a few slides. And this is where we did it in the last video with the classical approach. Let's go back to the actual problem, which is right here. Okay, so in this example, again, the same one from the last video, we're making pistons with a known historical data. The population diameter is normally distributed with a mean of 4.25 centimeters and a standard deviation of 0.12 centimeters. This is the distribution of individual piston diameters. From that, we take a sample of size 16 and we find a mean of 4.31. Notice that 4.31 is bigger than 4.25, but the question is there enough evidence to suggest or to support the conclusion that the sample came from a different population than the historical population? Or maybe if I were to rephrase that, is there enough data to say that something's happening on this machine to cause it to make different sized pistons, maybe larger or smaller pistons than normal? So if we summarize what we have, our random variable x is the diameter of an individual piston. X is distributed normally with a standard deviation of 0.12 centimeters. The null hypothesis is actually all of that, plus the fact that mu is 4.25 centimeters. The alternative hypothesis, H1 or HA, is mu is not equal to 4.25 centimeters, making this a two-tailed test. And then we measure our sample mean. The mean or average of our sample is 4.31 with a sample size of 16. We choose a level of significance, which is 0.1 for this one. Same as last time. So the probability of getting a sample mean as far or farther away from the hypothesized mean as what we measured, we actually got, the 4.31. What is that probability? Well, notice that 4.31 is to the right of the hypothesized mean, which was 4.25. So we're wanting to know the probability to the right of 4.31. So here I just did 4.31. I went way to the right, say 1,000. Something really should be infinity, but we can't put in infinity there. Of course, you could have used mean plus 10 standard deviations. At this point, that would have just been about 4.55 would have been just as good as 1,000 here. But anything, put in 10 there or something. Okay, 1,000 works. And so I'm finding the probability from 4.31 to 1,000, or basically to the right forever, with a mean of 4.25 and a standard deviation of 0.03. Now remember that standard deviation of 0.03 is not the sigma, not the standard deviation of the individuals, but rather the standard deviation of the individuals divided by the square root of the sample size. So that's 0.12 divided by square root of 16, which turns out to be 0.03. So be sure that you're using that standard deviation of the x bars, sometimes called the standard error, for the standard deviation here. And then we find that probability. So that's the probability we would get a 4.31 or something to the right of that if the null hypothesis is true. Now we want, since it's two-tailed, we want to also see what probability of getting that far to the left of the mean would be, which would be the same probability. So we need to double this. So we double this because half of our p-value as well as half of our alpha value is in each of the two tails. So when we double this, we get a p-value of 0.0455. So what this is saying is the probability we would get a mean of a sample to be 4.31 of a sample of a size 16 if the null hypothesis was true is about 4.55%, 0.0455. That's the p-value. It's the probability of getting something that level or more extreme. Now to make your conclusion, we just compare that to alpha. So the smaller the p-value is, the more likely we are to reject the null hypothesis. The less likely we are to assume that it really came from the null hypothesis distribution. So in other words, the smaller the p-value, the less probability we could have made a type 1 error. So the p is 0.0455. That's less than our acceptable threshold for a type 1 error, alpha, of 0.1. So we reject the null hypothesis in favor of the alternative hypothesis. Now, if we look at this picture, if we put the 4.31 right here on the distribution of x bar values, and we find the probability to the right is 0.0228, that's that norm CDF that we just did, we put an equal area mirror image on the other side of the mean down here, and add those together, we get our p-value, which was again 0.0455. That is less than the alpha. Okay? So we reject the null hypothesis in favor of the alternative hypothesis. So in this case, what does that mean? Well, we should stop making these pistons, figure out what's causing us to make different sized, in this case bigger, pistons. We don't want to just keep making bad pistons. We want to fix the problem. So here's another close-up view of that same graph. And the blue region is P. Compare that directly to alpha. Now this one gives you a side-by-side, or actually one on top of the other, comparison of the critical value method and the p-value method. On the top picture, we see the critical value method. We find our critical values, in this case about 4.2 and 4.3, so that to the right of the upper one, right of the 4.3, we get half of alpha, and to the left of the lower one, left of 4.2, we get half of alpha. That's 5% in each tail for a total of 10% total. 0.05 here, 0.05 here to the left, total of 0.1. That's the alpha value. And then we compare x bar to that. So we're comparing our x bar to these x bar values, to these critical values. The x bar is in the red region because it's to the right of the upper critical value, and so we reject the null hypothesis. The critical values are the boundaries of the red shaded region, and then when you want to see if the x bar is in the red region, reject the null hypothesis, or in the unshaded region, that would be do not reject the null hypothesis. In the p-value approach, the x bar is the boundary of your region, in this case one of the regions if it's a two-tailed, so that when you put the probability here to the right of it, plus the corresponding probability over here, you get the p-value. So we're really comparing the blue to the red area, or just really the numbers of the p-value to the alpha value. So it's a pretty easy way to interpret your conclusion, a very easy decision to make. If it's a small p-value, well, how small? If p is less than alpha, then we reject the null hypothesis in favor of the alternative or alternate hypothesis. If there is sufficiently strong evidence to accept the alternative hypothesis, and the probability that this sample came from the hypothesized distribution is below our threshold for an acceptable probability of a type 1 error. So the probability of making a type 1 error is small. It's really p, which is less than our threshold of a type 1 error, which is alpha, and so we reject the null hypothesis. If we have a large p-value, how large? Well, greater than or equal to alpha, we fail to reject the null hypothesis. In this case, there's not enough evidence, or at least not strong enough evidence, to support the alternative hypothesis. The probability that the sample came from the hypothesized distribution is above our threshold for an acceptable probability of a type 1 error. So the probability of making a type 1 error is too big. It is p, which is greater than alpha. There's a distinct advantage to the p-value approach. One of the reasons is the value chosen for alpha is somewhat subjective. Someone may have a different standard for what they feel is appropriate for the amount of probability we're allowed to accept for a type 1 error, which is exactly what alpha is. So if the p-value approach is used and the p-value is reported, then the reader of the study or whatever you're publishing can easily compare this to a different alpha value without having to redo the entire test. So for example, if I read a journal and they're using an alpha of say 0.1 and they make a conclusion based on that, as long as they do the p-value, if I say, wait a minute, I'm not comfortable with an alpha of 0.1, I want to use an alpha of 0.05 instead, or even smaller, 0.01, then I can compare that p-value to my alpha without doing anything else. And so for that reason, I and your calculators programmers prefer the p-value approach. So even though, so for example, if you were doing the critical value method and they reported the critical values in the test statistic, you would have to completely redo the test to find new critical values for the each alpha, because the critical values depend on alpha. The p-value doesn't depend on alpha. You compare it to alpha to make your decision, but computing the p-value has nothing to do with alpha. Now, there's some variations on a theme. In fact, we've really covered the big idea for the whole unit now. We know about confidence intervals, and we know about hypothesis tests. If you understand this, you understand the basic concepts for the whole unit. So there's some different variations on a theme that we could have here for hypothesis testing. First of all, the example that we did was a two-tailed test. The alternative hypothesis was that mu was not equal to mu naught. We could also do a left-tailed test where the alternative hypothesis is that your mean is really lower than the reported mean, mu sub 0. The alternative hypothesis is mu less than mu 0. That's a left-tailed test. Similarly, we could do a right-tailed test. The alternative hypothesis is that mu is greater than mu naught. Notice that these are not necessarily exactly opposite from the null hypothesis. The null hypothesis is always that mu actually equals mu naught. That's what we're actually assuming whenever we do our probability calculations, say to find a p-value. We're using the hypothesized distribution to do that. So we're actually assuming that mu actually equals mu naught, and we're actually assuming more than that. We're assuming that we're working with a particular known distribution. Now, so one variation on a theme is talk about whether it's two-tailed, left-tailed, or right-tailed on our test. But other things that we can do is we can have different assumptions, and this might lead us to slightly different test statistics or different types of hypothesis tests. We could even be measuring different kinds of statistics altogether. So we will have, for example, in this unit, I will be talking about doing hypothesis testing for means, and I can also talk about hypothesis testing for proportions. I can also talk about hypothesis testing for variances or standard deviations. And so those are like three different kinds of tests. We also end up having one sample and two sample versions of these things. But all of this are really just variations on the basic theme that we have here. And no matter how we do it, we always interpret a p-value the same way. It is always the probability of a type 1 error. Compare this to our threshold of the acceptable limit for the probability of type 1 error, which is alpha. So what is the p-value again? It is the probability of getting a sample statistic, in this case a sample mean, which is the same as what you got or something more extreme. Okay, more extreme. What does that mean? Well, in a two-tailed test, that means further away from the mean, either to the right or to the left, above or below the mean. If it's a left-tailed test, more extreme means further to the left, or smaller than or less than what we actually got. And a right-tailed test is further to the right, or greater than the value we just got. That's what I mean by more extreme. One thing that's very important is that we verify the basic assumptions for a statistical test. So before using any statistical procedure, actually before using anything in mathematics, we have to make sure that the underlying assumptions have been satisfied. So for any statistical procedure, it's important that we confirm that the conditions required for using that test are satisfied. Otherwise, the test is worthless. One common mistake is to blindly use some procedure when that procedure is not even appropriate. This leads to conclusions which are not valid and, depending on what it is, potentially even dangerous. So what are the basic assumptions for what we did here, a one-sample z-test, or earlier in the videos, a one-sample z-interval? Well, for a z-test, we're testing a sample mean against a known population mean. For a z-interval, we're forming a confidence interval for the unknown mean of a population. In both cases, the distribution of sample means has to be approximately normal. This is usually a good assumption if the distribution of individuals is nearly normal or the sample size is large, say bigger than 30. These situations of a z-test and a z-interval are very common in the sense that we are often are concerned about the mean. In fact, that's the most common type of confidence interval or hypothesis test. But there's a real problem with a z-interval or z-test, particularly z-interval, is that the population standard deviation has to be known to use this. This is usually not a good assumption. And so we're going to see how to correct that in a few sections below. But before we do that, and the way we're going to do that is with a t-distribution and get a t-test or a t-interval. But before we go on to that, we're going to follow up this video with a couple more examples of z-tests so we can get better at this before we move forward.